In this part of the video, we're going to talk about functions that is not element-wise functions or element-wise operators, such as reshaping function or like matrix multiplication or staking functions. The first part is that what I'm calling it the reshaping function. It includes families of functions that change the shape of an ND array. So now let's see a first example of reshaping and seeing how useful it is. So first of all, let's run above code and loading an image. This is an image that we use as an example image in last week, and we make it as an NP array by simply calling the NP array function to convert it. So we simply got array that represents these images. And we probably should see the shape and D types of this function first. Okay, using this one. Okay, so we see this array has shape of 530, 804. This is the height of the image and width of the image, and it has 4 channels, RGBA. Now suppose we want to see the numerical distribution of each color channel, that is RGB, red, green, blue channel. We can use the matplotlib function, hist, to see the histogram of each channel. However, in order to feed the data into the function hist, each of the components need to be a one-dimensional array. Currently, each channel, we have 4 channels, and each channel is two-dimensional array. Although we can simply do the things like, say, this one to get the red channel, and then maybe we can flatten it to get what we want. So suppose we feed this guy into the PLT hist, and we should get a histogram. Yeah, this is what we are seeing. This is a histogram. You can see that for each value between 0 to 255, it is on the x-axis, and the count of how many times the value appears in this image is on y-axis, and this is what we wish to see. And we can do something like to see the percentage instead. Okay, so we can see the percentage. I sort of forget argument to see our density. It's a density is true. I mean, I can choose density is equal to true, and the bins make more bins, and see the result. Okay, it's more like it because it used, I think the default is like 10 bins or so, but since we have like 256 different kind of level of in this case the rate, so this one may be a more accurate or more fine graph that we wish to have. And we can see that, for example, the most popular value of the red color is about 8/1000. The ratio is about 8/1000. However, this is not exactly what we want to see. We want to see all these RGB together. So how do we separate all these RGB channels at once and flatten them? So one way to do that is that, let me put it here. Let's first reshape it all together. That is at least what we can do here. You use the reshape here. So we don't have to flatten each of the channel separately. We can do it at the first step. So we do it in one step. And also, how do we separate them to each in different variables? Or we need to move this channel to the first place, because you can see that RGB is at the first level. So we should have array is the first dimension has 3 elements. The first axis should have 3 elements. So what we can do here is use the transpose. There are different ways to do the transpose. We will introduce a moment later. But currently we are using .t. That is a property, which is like the mathematical notation. So let's run the transpose here. Maybe you should see the shape of it. So you can see it's as our wish that it become the shape of 4 and by a big array right here. Then we can use the tuple deconstruction semantics in Python to separate all these 4 channels into different variables like RGBA here. And we can do the histogram of all of them. And here I also assign the color of each element to have their own rightful colors. This may not be the most elegant way to do the text that we are doing, because in fact, NumPy does have some functions that to separate each channels into different variables, that is, destruct each channel. But I think it already demonstrated that reshape is a fundamental operator that can be very useful. And in fact, if you have been doing deep learning, you probably have encountered some operations that need to do the transpose or reshape already. Like if you are using PyTorch, the image has to be channel first in PyTorch convention. So you have to move the channel from the end, which is a common convention for image representation in NumPy array, to move that channel to the before the height and the width, the axis of height and width. And you probably also have some batch dimension at the beginning. So you probably have encountered situations that you need to manipulate the shape or axis of the array. So let's see more of this kind of operations. So let me get the image array again and see its shape. So one thing we want to do is to add one more dimension to the beginning so that it becomes a batch of images. Although we only have one, but in some function it requires to take an input as a batch of things. So even we only wish to fit one input it, we have to construct a batch that contains only one element. You may think that's simple because we can simply do like 1, 5, 3, 0, 804. This might just work. And you see, actually it is work. But come to think about it, it seems to be a little bit complicated because we have to already know that the shape of the image array is this guy. But we probably cannot know it beforehand. So we think, okay, that's still easy. I can do things like this one. Plus image array shape. So we change the shape to have one more axis that is exactly one, and we got the things we want. Okay, but this one is a tuple. It's not a big deal. We simply use the right type, and we got what we want. That's true. You can use this method. It just we have some easier method to do so. So one way to do that is this function. We use none here. At least if you don't know what it is, it may look a bit like magic. Let me just see its shape. Okay, so you can see that comparing to this one is much shorter and does not require some computation. You need computation here. Don't take me wrong. The computation still has to be done, but just they can do it automatically in the function itself. So what does it mean? It means we give one more new dimensions right here, and the dot 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 means pretty much the original dimensions. You can do the same thing this guy using this syntax. Use command here. This still works, but nevertheless, the none means the new axis. You may think that the readability seems to be a little bit decreased because we are using a none and nobody knows what none is. If you think so, there's an alternative way to do so. That is, we can replace none by np.newAxis. In fact, I think np.newAxis is just the alternative alias of none. So you can say that is true. It is simply just a none. But instead of writing none directly, this one can be more readable. And we can put command here. Command means just one dimension, just like the slicing. But by using command, dot 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 means all the commands, pretty much equivalent to things like this one. But you don't need to worry about how many axes it has. So they are a little bit different, but they look the same. But when using the command here, there's one benefit of it because you can do things like this one. So we can add the new dimension at the second place, and if we can actually omit this one and have the same thing. In fact, you can just omit everything here and make a new dimension at the first place. And you can have two nonce here to have two new dimensions, and maybe add a common here, and has the new dimension right here and here, and put it right here so that we have new dimension here, and yeah, I think you probably got the idea already, but I'm just doing one more example. So after this experience, you'll probably get the idea. And if you haven't got the idea yet, just try it a little bit until you get it. Another way to expand the dimension of array is using NP expand dimensions. So it might be more readable or more elegant. And we can put the axis to be -1, so it can be last, and put it at second. Or even you can do things like 1, 2 to have two new axes. If you are using PyTorch, equivalent way to do expand times function is unsqueeze. It's like there's an unsqueeze function. And NumPy also has a squeeze function. So we can reverse this process, which is sort of like the squeeze function in PyTorch. I still need to see a shape. We don't need to see a content, we just need to see a shape. So you can see, where is it? Here. At the beginning, we expand the dimension to two places, and then we squeeze it back. So every dimension that has every axis that has only one component, one element, then it will become eliminated, deleted. So that's squeeze, or we squeeze out the dimension that is only one. So it remains to, now let's talk about the transpose. As we can see that when we have array, when we have a metric, then we can use a .t to transpose the metric. So for example, our image array, we can .t. Image array is not metric because it has 3 dimensions. But if we use the t, you can see that it moves the last one to the first one. It moves the last channel to the first channel. It is arguably the right semantics because a metric transpose only applies to metric. So when you have a higher dimensional array, the right interpretation may be a little bit ambiguous. So there's a function to specify the details. That is called the np.transpose. So you can see that we have 3 different axes. Then we can manipulate this axis at our wish, at our will, as we wish. You can see that we have 0, 1, 2 here. This is the original one, so it does not change anything. But if we move this 2 at the beginning, then you can see that the last axis is moved to the first place, and we can put any permutation we want, and you can see it's pretty straightforward, and because we can given it arbitrary permutations, so it is very powerful and can suit any of your needs. So basically, you can do any shape manipulation and rearrange the axis at your will. You can do that by using transpose and reshape. It's just that there are some functions to simplify the task, to simplify some common tasks. Okay, let me show you just one more example. First, let's see the array here. Okay, maybe we should just see it as an image. Okay, so see, we wish to have make this image become 4 smaller image, but the first one is on the upper left, upper right, bottom left, bottom right. Have 4 small copies of this image. Not exactly the copies, but because they are smaller, but we wish they pretty much look similar to us. So let me see, let me do it and you can see what I mean. So let's make this one as image 2. So first of all, let me reshape the image array to different things. So we have 250 and 2 and 402 and 4. Recall that the original shape, this one might be, I didn't bother to actually calculate the result. I just divide it by 2. Maybe this one should be easier by or more symmetric to put simply 800 by 2. No, this one should be 530 because I already changed the axis the right shape should be this guy. Okay, so let me first do this together. And you can see we probably make a mistake all the time to just forget how to put the shape at the end. So it will print a lot of garbage. So I have to scroll up all the way up. This is probably not what I want. Okay, just do it. So we got the shape we want to have. And now we want to change it a little bit so that, first of all, I can move all these to at the beginning. So we can have four smaller images and we can show them separately. So let me first to transpose. So here we also demonstrate that you can call the transpose as a method of the array. You don't have to put np transpose at the beginning. So what we want to do? I always put all the dimensions in order here. 0, 1, 2. How many dimensions how many axes do we have? 1, 2, 3, 4, 5. I always put them in order at the beginning, then do the arrangement. So what I want to do is this guy to the front and this little guy to the front. And then we reshape it to become, let me put it into another line. Reshape it to become 4 and okay. So let's see the shape. Okay, that's what we want. We have 4 smaller images, but are they looks like a small version of the original one? Let's check it out. So let's call it IA2, image array 2. And for I in range 4, let's show the image one by one. Okay, we have a show already defined. Perhaps it's defined, I'm not sure. I have already called a function yet, the definition of a function yet. But we still need, let's just see it. Okay, we don't have it, so I should write it from scratch. From ipython.display, import display, and we simply display image from array. So it seems works just fine. We have 4 small copies of the original images. And then we will to combine them together and not doing it brute forcefully. We do this again. Maybe we should just copy the whole cells. And let me make a new cells below and paste code here. Let me do it in one step. So we simply move this again. We only need a transpose and the reshape. But right now I simply move this 1 before this 0 again, and move this 3 before this. And instead of making 4 images, I'm just having 1 and has the original size. Okay, so let's see. Yeah, what I got what I was meant. I got what I say I want to do. We have 1 image contains 4 small different images. If you understand how it works, it can be handy and helpful for you to do things. In fact, in deep learning, there is a thing that called the pixel shuffle. That is usually be one of the layer to do things in super resolution, an image. Kind of like convolution, but it transforms a small layer into a large one. It combines convolution and some operation like this one. Not exactly the same, but have the same idea to manipulate the axis and resize the images. Another common operation we do is to stack several arrays together along some axis. So let me show you some examples. Okay, maybe I need to go back to the definition of this show and run it. Okay, so then go back. Control O, does Control O works? No, Control O does not work. Control O serves as the go back to the last position in VIM. So I'm using the VIM theme key combination, but key bindings, but it does not work on the Jupyter notebook settings. Okay, let me show you how does it mean by stack. So we have one function called hstack. That stack means combine these 2 arrays together one by one along one axis. So h means horizontal. So hstack, when you apply to an image, you can visually see that we are merge these two images together along the horizontal axis. Similarly, you can do this the vstack. You can use a vstack, which means vertical, horizontal, vertical combination, vertical stack. So you can see that they stack vertically. It works as you expected. You can see the shape. If we do vstack, then the first axis will sum up together. And if we do the hstack, then the second axis is summing up. Because we are stack two same things together, so you can either stack it at vertical or stack them on the horizontal axis. However, if you are not stacking the exactly same shape array together, you have to note that along the other axis, along the axis other than the axis that is being stacked, all of the shape has to be the same, except of course for the axis that is not be of course except for the axis that is being stacked. Another function is called the concatenate, which we concate two things together. You can also do that. So for example, in this case we concate them, but we make the other flip one of the image together, so it will have a mirror, left to right mirror effect. Because we are using concate, and we can specify the axis, so they do the same things. They do exactly the same thing as the horizontal stack. There is also a stack function, np.stack, which you can also do it on other axes instead of horizontal or vertical stack. Another way to do stack is not using these guys, but simply convert a list into, let me show you. We have two things right here. I can simply convert list of arrays together. So you can see that we have two right here. We can concate them together, but along with a new axis at the beginning. So if this is what you want, then you can simply use np.array. But you can also combine it with the transpose. Let me transpose it to what? Again, I always write everything in order at the beginning. Then I move the things I want to where I want it. So I move it to here, and then I reshape it to be like this one. So I call it IA2, and let me show you the IA2 here. Okay, not correct. Which maybe I should check the IA2's shape first. Oh, I know. That's a common mistake. I forgot to remove the shape here. Okay, so this should work. Let's just show it. Okay, so we got the same thing. So if you forget what the concate or vstack or hstack, and just think they are too complicated and forgot the usage, and you don't have AI to assist you writing code, then you can simply go back to the basic principle of construct list into an array and transpose and reshape using these all fundamental operations, combine them together. Surely it is more ugly and not elegant, but they work just fine. Okay, so let's focus on the functions itself. As we mentioned before, a lot of function is work element-wise. In fact, there has a name called ufunc. Many useful and common functions are not ufuncs. The following is a few examples. For example, the maxima of things. It does not make sense to work element-wise, so it just pick one of the largest element in the array, and of course summation. Or in the statistics, we wish to find the mean of values in the array and the least element in an array, such of things. So for the image, we can do some interesting things like finding the vertical or horizontal averages and a lot of different things. So this is one of the things I do on the example image. That's just a simple experiment and make the picture a little bit artistic. As you can see in the shape, so we can do the average or the mean along the first axis or along the second axis. We can do it along the last axis. If it has only RGB, then it will become grayscale image. But we have a better way to do that by using the method functions in the next section. So that's just some functions that appears in NumPy libraries. That is not a ufunc. There are a lot of functions appears in NumPy libraries. So I cannot give you a complete list of them. I'm just giving you an idea that there do exist a lot of functions that is not element-wise applied to an array. So when you encounter some functionalities that is not element-wise but is working on a NumPy, if you search for NumPy and such functionality, there's a good chance it is implemented in NumPy. It is already exists in NumPy, or you can find out some like articles or blog posts or some question answers in Stack Overflow that show you that you can complete your task by combining several NumPy operations or functions. And nowadays you can use AI and ask AI whether there are some functionalities appears in NumPy library. But the thing is, you have to have an idea is what is the capability of the NumPy library. So before you even doing the search or doing the asking, you probably will have an idea of how likely this function is exist in NumPy libraries. So currently I'm just giving you a very small list of things that appears in NumPy library. I'm just giving you a mean. I haven't even given you the standard deviation. You can also do the standard deviation. You can do the median. And one of my favorite function is interpolation, 1D interpolation. That is, by given some sample points, we can find a function that fit this sample point. And it also has some function to do linear regression. It can do a regression. It can do function fitting. But the function fitting function itself is in SciPy. There is a better SciPy function that can do a better function fitting. Sort of like machine learning or even AI. You can do some basic stuff using this functionality. So just as I just mentioned, one of the brother library of NumPy is the SciPy. It contains a lot of different functions that works on NumPy and in the domain of scientific computing. So you are going to find a lot of different functions in SciPy and NumPy. So as a student of learning NumPy, as a beginner student of learning NumPy, I think one of the best things you can do right now is when you try to solve a job or task, always ask, does NumPy has this functionality? Does SciPy has these functionalities? And after a while, you are going to get a feeling of what functionality should be in NumPy and what kind of functionality should be in SciPy, and which functionality you won't have much luck to find them in NumPy. Next, we are going to talk about tensor product or matrix product, matrix multiplication or inner product. The simplest form is a dot product, which we've learned in maybe in mathematics class. So basically, you can use some fundamental operators like element-wise multiplication and using sum that we just have learned to do dot product. But because they are just so fundamentally exist in mathematics and in a lot of things like in scientific computing, so we do have a dedicated function dot to do these things. So in fact, indeed, they are just doing 1 times 4 plus 2 times 5 plus 4 times 6. That's all. So we can do it using the element-wise multiplication and using the sum. But does has a function called a dot to compute the dot product. So one benefit of this function is it is shorter, and also it may be much efficient because we are using it a lot. So efficiency does matter. It also has operator symbol, which is introduced a little bit later in the Python development history. I think it's no more than like 10 years, but I can get it wrong because time just flies so fast. But originally, there's no such operator, and you can see this operator looks a little bit funny. I mean this operator, like at symbol. This operator seems a little bit funny, but because people just use the dot product just too frequently, so that this np.dot is not enough and doesn't look that good. So people want this operator dedicated for the inner product. So we have this operator right now. There has some other options considered, like using a Unicode of the cross sign or or using multilaters operators instead of this strange operator. But it turns out the Python, maybe Python Software Foundation or Python core developer, they decided that this one looks better by consider all pros or cons. This one is a winning choice. So we are stick with this symbol right now. And I think it turns out good. People used to this symbol. Although it doesn't look very mathematical, doesn't look the symbols in mathematics, but still people are used to it. And I'm happy for it. So you can see that they actually works the same. However, since it's going to get a little bit complicated when arrays beyond just 1 or 2 dimensions. Because if you are just in 1 or 2 dimensions, then we can do the matrix multiplication or matrix factor product or factor to factor product, which is just the inner product or dot product. However, if we are considering a higher dimension array, things get more complicated. So in fact, there is a thing called the tensor dot, which can do it. So you can see if we have 3, 4, 5, the array with a shape of 3, 4, 5, and another array with a shape 4, 5, 6, and we do the tensor product, it will become array of shape 3 and 6. That is the 4, 5, this 4, 5, and this 4, 5 are summation up together. So they disappeared. So we only get the 3 and the 6. Kind of like the matrix multiplication. It works on 2 axes. And we have things called the matrix multiplication. If we have something A and B which has a shape 30, 4, 5 and 35, 6, and we can do the matrix multiplication and get array with the size of the shape of 30, 4, 6. Basically, it does is a batch matrix multiplication. That is, we have 3 matrix in the form of 4 by 5 and 3 5 by 6 matrix. We do them one by one. So these examples give you an idea that we may have some different interpretation or generalization of what does it mean by the matrix multiplication to a higher dimensional array, because there are just too many different generalizations. So how do we choose the right one and tells the NumPy to compute the one that we wish it to compute? That is sort of a difficult decision. And in fact, it is something you need to be really careful, because we have a lot of libraries that sort of similar, like PyTorch, TensorFlow, and NumPy. So what is this library's design choice for the tensor dot or dot? It is not entirely sure, because people can have a different choice of design of a library. So you have to always read the document or maybe do some experiment to actually see what the dot means in this library for higher dimensional array. They always works pretty similar when it applies to like 2D array or 1D array, that is to the matrix or factors. But if you are having higher dimensional array, they may have different behavior. And they are not just designing this behavior to upset you, to make your life to be more difficult. It's because this library, although they are pretty similar, they are designed for different purpose. PyTorch and TensorFlow are designed to work for deep learning neural networks. So they have to consider the batch of things firstly, because it happens a lot. But in NumPy, the batch product is the batch process is probably not the most important things to be considered. So they have different design purpose. And the TensorFlow and the PyTorch, originally they have different design philosophy. So that may lead them to have different choices. Also, there are one of the library that called JAX is also popular. Although it is designed by Google, just like TensorFlow, but they have a very different design choice. So the thing is, when it comes to the things looks like a matrix product, tensor product, tensor dot or dot, just be careful. Some operation may be more difficult to do in one framework than the other. Okay, so we have different things right here. Before we go to very useful solution to the above issues, I'll just remark here that if you are not familiar with metric multiplications, here are some resources you can find out to visualize the metric multiplication or just to review, to recall what it is. I have some interpretation that is very more intuitive in interpretation of what metric multiplication is. I summarize in here. It can be considered just a weighted mean or weighted summation over a factor. That's one of the point of view. A lot of people like this point of view, but there are more of them. Like it can be considered as a substitution into a system of linear equation, and you can see this in my company Jupyter notebook here. But this one is written in Chinese, so although I think it might also work for you, but just maybe you can try it or to see if it works. And if you are more coding guy, a programmer, maybe you can understand this operation, metric operations using the NumPy terminology. That's as we have introduced some notation like NP, new axis, these kind of things here. And you can use this to learn what it exactly means in metric multiplications. It has defined right here. If that's a better way, I mean easier way for you to understand algorithm. So some of you may be not comfortable with mathematical formula or the writing convention of mathematical formula. You think it's just too scary or maybe for other reasons, and does not learn metrics or linear algebra very well. But you can actually understand this operator. I mean, how does it compute by using the code right here. If you understand what the NumPy works, you can see this. We only use the very simple operators like the element-wise operator and the sum here, so that you can understand them. Now we are going to introduce general framework of generalization of how to do these operations. That is using the tensor dot. So tensor dot is a more generalized version of the metric multiplication. In fact, it actually just defined in two operations. One is, you can see the combinations. Suppose like we have two arrays. One has a shape 3, 4, 5 and 4, 5, 6. A tensor product is combined with two operations. One is just consider these 3, 4, 5 and 4, 5, 6 together. And the other is the contraction. That when we mean the contraction, it means we sum up these guys along this axis. So here we have a 5 here and a 5 here. We can pick the first one of these 5 and sum them together, and pick the second one and the third one to the fifth one and sum them together. And we do this for each of these 3 elements, each of these 4 elements, and then each of these 4 elements, and each of these 6 elements. So we do it a lot of times, but the 5 has been eliminated because we sum them up over these 2 axes. So of course, 2 axes has to be the same size so that we can contract them. And we can contract these 4 and 4 together, and so that both of these 4 and 5 are eliminated, disappeared. We only get these 3 and 6. And we are doing this contraction for all possibility pairs for these 3 and these 6, because there are no pairing. So you have to do them for these all total 3 times 6, 18 pairs. Also, that's the idea of what it means a tensor dot in this context. There are some mathematics meaning of tensor product and things, but for what we use in neural networks or in in the scientific computing, this tensor contraction is the mathematical origin of those operators, and we only use this kind of things. And of course, like the dot or metric multiplications can be considered as a special case of tensor dot. However, we can still do a even more generalization called the Einstein summation or Einstein notation. So you can check the Wikipedia here and see what the Einstein notation is. This, if you have to learn just only one thing, then you can learn the Einstein notation. And you can use this Einstein notation to replace all of these operations by giving a specification in the Einstein notation to look like a signature of the operation. You can simply give the signature, or maybe you can fill it as a specification, and to describe the operation. And by using this description, you can describe all of the common operations on matrices or on arrays. So for example, you can define a trace, a diagonal. The trace is a summation of a diagonal. And the diagonal means we just ignore all the elements except the diagonal and become a vector here. And the dot product, as before, the tensor dot or matrix multiplication. You can check this simple exercise, this quiz here. But before we end this session, I'm going to give a small introduction and explanation of what tensor dot is. It is not that difficult. Let's just go to this guy. So you can you can read the Wikipedia to understand it more thoroughly. But I'm going to give you simple slides for showing it. Okay, so this is quick introduction to the Einstein notation. It is also known as Einstein summation. And in fact, not only NumPy provides this functionality, there's also a popular library for PyTorch to do Einstein notation. So if you know the Einstein notation, you can use them to do very efficient computation and to understand other operations. You have a language to describe, like we say, every library may implement the tensor dot differently, so they have different behavior. But which behavior they are choosing, we can actually using the Einstein notation to describe a certain behavior. So it is notation convention, and originally, because it is invented by the Albert Einstein that you know. There are a lot of different Einstein, but this Einstein is the Einstein you know. So it used a lot in mathematics and physics. It simplifies the complex mathematical expressions to be more concise, so that you can, I think it helps you to understand the formula easily. But in fact, I doubt that if you don't understand the inner product and dot product, it may be still a little bit puzzle to you if you're reading this notation. But once you understand what dot product is or matrix multiplication is, this will vastly help you for understand more ideas. So if you are not familiar with the matrix multiplication, you should understand them first before you process ahead. So for historical context, it is introduced by Albert Einstein in 1916 and first used in his paper General Relativity. Okay, so it is quite famous and popular since this paper has been published. So it quickly adopted in physics and mathematics for its elegancy and efficiency. So what does it is? Basically, if we are consider of the inner product or dot product example, like this one, mathematically we can write down this in these two forms, in the summation form, or if we expand it you can write it here. Although the summation form is already quite concise, but some people may be more comfortable with this guy. But sometimes this way of writing things may have some ambiguous. So to be more formal and strict, we usually write it in this form in mathematics. But when we teach things, we usually just explain it to help student or listener to understand it easier to understand it, because sometimes we cannot assume that people are familiar with this formula. But anyway, these two are the same and is standard way of writing things. So what is the Einstein notation? That is, by using this convention, we can write the formula, the summation in this way. The thing is, they are the same. We just omit the summation. And by knowing this is Einstein notation, we know that this guy has an I here and has an I here. We know that suppose we have an index that appears twice, then there should be a summation over all the domain of all the range of this I. So that's it. We simply write this thing and we just omit the summation symbol here. And we know that whenever we have 2i or 2j or 2 anything together, we sum them up. Sometimes in some situations, only one I is on the subscribe and one I on the superscribe can be contract or can be sum up together. Okay, so I use the term tensor contract here. So because this is exactly the contract. Sometimes it requires to be upper and one is on the top and one is on the bottom. One is a superscript and one is a subscript in some convention. But in a more relaxed form, if the I appears anywhere, then we do the summation. So for example, these two equivalent, just one is in Einstein notation and the other is in the usual notation. This guy omit the range of j, but you can see that the I does not affect by notation because there's only just one I. So the I, we keep the I here. So we have a vi equals to this guy because there's no just one I here. So you don't need to contract or like the sum up the I. But for j, they have two j's here. So when we write these things, we mean these things. So why does it so elegant? Because when we write this matrix, vector product, we can write in this way. So one is a column vector. You can see the vi here. For every column vector, we put the index on the superscript. And for the row vector, we put the index on the subscript. So although these two things look similar, but because of the different position of the index, they are different. So just give you an idea of why we sometimes put the index on the subscript, and sometimes we put in the superscript, because they actually live in a different space. The column vectors lives in a space. The row vectors in another space. Although they have the same dimension, they have to have the same dimension. Otherwise, they cannot do the inner product. But they actually formally they are in different space. So in some mathematics or physics context, these differences are very important. One is considered as a function and one is considered as an element. So we have to do some operation to swap their roles. However, if we are only consider about computing things, this restriction can be a little bit relaxed. Okay, so for the example, for matching multiplications, if we already know everything, we can write the matching multiplication in the Einstein notation in both of these forms. One is using the more strict form like superscript and subscript convention here. So you can see that the j and j are cancelled out together. When I say cancel out, I mean contraction, the summation up. So if you are thinking more programming, like a writing program, this is a for loop, and we sum them up. However, sometimes we just relax the rule a little bit, so this one is also correct. And we're probably just using this convention here, because we are not differentiating cospace, cotangent space, all these different functional space things. Okay, here are some examples. That is from menu of NumPy instance. So suppose we have some arrays here, A, B, C here. It has array 5 by 5, 5, or 2, 3, and we can do something here. So for example, if we want to do the trace, you can see that we can simply use Einstein sum II A here, because you can see that this is just a for loop, and for each I, we take AII. Remember that A is 5 by 5 matrix, so AII here means because we have two I here, so we must have for loop and do the summation, and it is for the I index. So this is the trace. We can directly call a trace here. The second one is the alternative forms of Einstein sum here. But I think at the beginning you can just skip this one and stick with this guy. This one works just, I think most of the case we are using this kind of form. And we can also extract it diagonally to get the diagonal. So the first one and the second one are similar. But in this one, although we have II here, and we do have a for loop here, but because we are assigning the output to be I here, so they do not sum them together. We simply pick the AII and assign it to the ith element. So here is some variation that we haven't mentioned before. Because we have an I here, so this II does not take the summation for all the range, because we have to have this I outside here, outside as an output. So each I corresponds to only one I. So we got the diagonal 0, 6, 12, 18, 24 here. Exactly the same if we call the diagonal function directly. So here is the alternative form. Again, you can stick with the form here. After you understand this form is pretty much the same. Okay. So for a more complicated way to do that is like IJI. This is just sum over an axis. Because there is a J here and our output has only I here. So we are doing this one. So each I will loop over every J. You can read like this one. There's more formal rules for these notations, but I think at the beginning you simply learn it by experience. At some point, you might be able to learn it by reading all the rules and in your head and compile them, and you know how to do everything. But for most people, I think you just learn by examples and you deduct the rules by yourself, and probably you will find out, okay, some corner case you're not familiar, you're not sure. Then you look the rules to check the corner case. That's the right way to learn it. If you have the ability to read the whole rules and deduct everything, then you probably should just go to read the rule. But I think it's still, even if you have this ability, it still can benefit you to see this example first. Okay, so if you have ij to I these things, then this one is just sum over of the one of the axis, sum over the j axis, the second axis. Okay, so one thing is that we use ijk as the axis, the convention of different axes. So I is the first axis, so we can also use ji here to compute the transpose, or specifically use ij to ji. This is more precise, explicit. You can use this one. Okay, there are a lot of examples on the menu page, on the web page of. I'm just picking some of them, so you can read all of them to understand that. But I think this one is very useful and helpful, because as we mentioned before, there's a library for PyTorch that do the Einstein notation, and it's very popular. So if you haven't done this before, I strongly recommend you to familiar with it. It will become one of your most powerful tools doing the data analysis